Just in time. So today we're starting the pressure temperature phase diagrams. So we did phase diagrams with pressure volume. So pressure is y-axis, volume is the x. And then your labs, y'all worked with that, at least the Monday labs had it this Wednesday. You'll work with the pressure volume phase diagram. So you'll be correcting the van der Waals equation to make it look like it has a vapor-liquid equilibrium region. And we'll talk a little bit about that today, but mostly focusing on the PT, the pressure temperature phase diagrams. Now, this one is typically touched on in freshman chemistry, but like all things that were that long ago, you've probably forgotten. And so we'll go through that again, and hopefully you'll say, oh yeah, I found one brain cell that kind of remembers what that chart looked like. So let's jump in. So this is the pressure volume phase diagram that you guys have been working with. Let's review just a little bit and walk through these different paths of change, physical change in these different phase diagrams. So let's take these different paths. Let me move my chart around here. Y'all mind if I sit? It's a little easier for me to look at this and draw on this tablet if I'm sitting down. And Michaela, can you hit the middle switch? Yeah, that's good. Okay. So what we're going to do is the path A here. Oops. No, that's not what I want. Whoa. Let me scoot over here. Okay, here we are. Path A, we'll put in this little piston here. And we'll start out with the piston way down here where we only have solid in here. So the piston's way down here at this point. Right here. So I'll just put a 1 there, and I'll put a 1 here. Okay, do y'all see the connection? And if I'm down there, I'm all in the solid region, and so this is just full completely with solid. I'm drawing little like crystal grains in here where it's all solid, and you've got some amorphous phase maybe around it, and so on. So you see over in that region, we are solid only. Is everybody cool with that? Okay, so we're going to increase the volume. How will we increase the volume? Well, we can change the volume with that piston, but we're also going to, in order to keep it at equilibrium, we're going to warm it up. So when we're going to the right, we're warming it up and increasing the volume, but we're staying at the same pressure. Makes sense? If we increase the volume, if a gas, if you increase the volume but you don't change the temperature, the pressure will drop. If we maintain the same pressure and increase the volume, we've got to add temperature. So going to the right, in this particular case, we're also heating it up. But you can't see that in a PV phase diagram because all you have is P and V. So there's a temperature axis somewhere. We just don't see it, okay? So we come up here, we move this up a little bit. Let's draw another piston line here. So this is the little piston. We'll call this 2. And now we're inside this solid liquid equilibrium region here, 2. This little gray stick. And there we still have the solid, but we've got some liquid. So we've got grains of solid. And I'm just drawing them with irregular shapes, and then we have some liquid, which I'm going to draw like little waves in here. But we don't have a meniscus, so that's kind of misleading. We don't actually have waves because there's no meniscus. It's liquid and solid inside the container. So if you were looking there, you would see the grains of liquid. If you shook it, they would move because it's a liquid that they're in. Okay. Then we get to this point here. This is point number 3. So we would draw this here. We're quite a bit larger in volume, and now it's all liquid, but no gas. So you would look in there, you would see a homogeneous phase, no meniscus, no solid. Shake it, nothing happens because you can't see the molecules moving around, but it's all liquid at point 3. And you can see that in the phase diagram. You see that far left, solid. Then you have this equilibrium region where you have solid and liquid. It's a melting and freezing in equilibrium. And then you have all liquid. And then you get to 0.4 here, where we're in the liquid gas equilibrium region. So we'll move this up here. And now we have a meniscus. And that's the vapor liquid equilibrium region. So this is VLE. And you'll see that in the literature and online and so on, talking about VLE plots and VLE this and that, talking about vapor liquid equilibrium. So how much vapor, how much liquid you have, that's where you are on this particular line. If you're over, let's see, where's my pen? If you're over here, if you're at this volume here, it's all gas. If you're over at this volume here, look where I'm at on the screen, then this is all liquid over here. This is all gas over here. If you're somewhere in between, like say right here in the middle, it's 50-50 on a mole basis. So half the moles in the container are gas and half the moles are liquid. That doesn't mean the volume is half and half. I mean, that means that the volume of the liquid would be really small, because you've got a small number of moles in the gas and the liquid. The same number of moles in the liquid take up less space, is what I'm trying to say. And then if we get up past here, past 4, we're at 5 over here, and we're all gas. So up here, 5, all vapor. So that's moving along that green line, along A. That's what that first piston did. We just opened it up and warmed it up, and it melted, then it boiled, and now it's all gas. And we could just keep going. If we keep increasing the temperature and increasing the volume at that pressure, we would just get a hotter and hotter gas. Let's do B now. So let's put B in this piston. Down here in 0.1, we've got it all compressed and it's all solid. So we've got grains here and maybe some amorphous phases. Then look at the range here. We have a huge range. This is all solid at this end here. This is all gas at this end here. Anywhere in between, you're going to have some proportion of solid and gas in equilibrium with each other. So this is sublimation. Think about dry ice. You've got a solid dry ice going straight to gas, CO2. And so if you're here in the middle, let's just pick this spot here. That's 0.2. You've got vapor and solid. In equilibrium. And then if you come out to 0.3 here, it's all vapor. So does that help with this pressure volume phase diagram? You understand all the different regions. In your lab, you're only dealing with this piece right here. So your lab deals with this plot right here. Okay. And you're looking at those isotherms that come up here like this, and they hit that spot, and they go straight across, and then they go up like that. So those are the isotherms that you're drawing in the lab. Okay. So that puts your lab in context. Now over here, we could do letter C in this container down here. Now we have a fixed volume. And we're going to do what they told us never to do, and that is heat a fixed container, like a container with fixed volume. Okay, so we start out, like, let's say it's CO2. We start out with, some solid in the bottom and some vapor in the container, and that's down here at 0.1. And then we start to warm it up, and the solid all melts. And so we still have vapor in the container, but then the solid melts. And then we have a meniscus. And so in this orange region, that's situation 2, where we have a meniscus. And then as we keep heating it, that meniscus starts to shrink, or the liquid starts to shrink, right? If you're looking in the container and you're warming it up, the liquid level drops and drops and drops and drops until it goes away and it's all vapor. How is it that we see the liquid dropping and dropping in this container? Well, if you look at the phase diagram, try to find my pen. Okay. If you look at the phase diagram, notice that we're over kind of on the right-hand side of this vapor-liquid equilibrium region. So we're closer to the gas side of things. And as we heat it up, look how we get closer and closer to the right boundary. And the right boundary is all gas. So at this point right here, the last little drop of liquid evaporates. And that's the temperature at which it all goes to vapor. But it's been boiling this whole time. So how can it boil at all these different temperatures? Well, it has different pressures. So the boiling point is changing as the container gets more and more pressure. So it starts boiling here, right here, it starts boiling in the vapor-liquid equilibrium region. Okay, and it's going on and on and on, and then it just eventually runs out of liquid. And so now it's all gas up here. So now if we shrink the volume down and we get above the critical temperature, below the critical volume, and above the critical pressure, that's the supercritical fluid region. So it has to be up above the critical point and kind of to the left, so it needs to be compressed in a small space, and it needs to be at a high pressure. So that's when it says supercritical fluid, that's the region for supercritical fluid. So that's the PV phase diagram. Let's do the same thing, but with the PT phase diagram. Okay. All right. So look at the axes. We still have pressure on the y-axis. Temperature now is on the x-axis. We have 1 atmosphere labeled on there. And so we could come across there, since we typically deal with 1 atmosphere of pressure, where you have the solid liquid equilibrium. That's the melting point, the normal melting point. So Tm, the normal melting point. And then Tb is normal boiling point. And that's where 1 atmosphere cuts across both those lines. Pretty obvious? Okay. Now here's our different paths. Here's path A. So what we did in the previous phase diagram, I've kind of tried to draw the same phenomenon. So this A line goes through here. And so over here, the same points apply. So if you can see your little piston diagram, over here at point 1, we're all solid. This is point 2, where we have solid liquid equilibrium. What we can't see on this phase diagram is volume. So we sit right there at the solid liquid equilibrium line until the volume changes, until we have all liquid. So we pause there, and that's why there's that melting point. So always in that solid liquid range, we're melting the thing the whole time. And once we get to the edge and the PV phase diagram of all liquid, we're done melting. There's no more solid left. And then we start moving across this temperature axis. And so then this is point 3. Let me just make sure I'm getting the same points associated with this here. Yeah. So point 3 was Okay, all liquid, yeah. And then 0.4 was the VLE, the vapor liquid equilibrium. Yeah. 0.3 is all liquid. And then we come across here to 0.4, where we're in the vapor liquid equilibrium. So in the PT phase diagram, it's just a single line. But we sit at that line until all the liquid's gone. So it's boiling the whole time. Boiling, 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 boiling until we run out of liquid, and then it starts moving into the gas phase. So this is 0.4, and then in the gas phase, we're at 0.5. Now, if I just give you a blank diagram and ask you to label the phases, how are you going to do that? I mean, you can memorize it, right? But what's a quick way to help you memorize it? Think about high temperature. What are substances, if you really crank up the temperature, what phase are you in? Gas, right. So you can label the gas first. So gas is at high temperature, low volume. I mean, high temperature, low pressure, right? And then if you crank the pressure up and cool it down, you're going to have a solid. So that's how I remember them. You know, the highest pressure, lowest temperature substances, that's you cool it down, it liquefies, and then it solidifies. And then that's where you have your solid phase. And then in between solid and gas is liquid. So liquid is in the middle. Okay, let's do the piston B diagram where we're down here where we have sublimation. So in 0.1, we're all solid. At 0.2, we were solid and gas. So straight from solid to gas, the sublimation equilibrium. We sit there until all the solid's gone and we become a gas, and then we're over here at 0.3. Where it's all vapor. Now, the strange one where we're sitting in a fixed container and warming it up, the pressure is changing because we're in a fixed container. And so notice how both of these are isobars. They're the same pressure. Okay. How do we draw one that changes pressure and temperature at the same time? It's a diagonal line in this. So this would be the line for, let's see, why is it not doing it? Oh, gosh. Yes. Okay. Terrifying. All right, here we go. So now we've got, this is C. So piston C. It's really not a piston, it was container C with the little flames underneath, where we started down here and we were at down at the solid liquid equilibrium. So it was 0.1 here, and then we were in the vapor liquid equilibrium, 0.2, and then we exited it into the full gas phase, 0.3. So it looks like, I mean, we exit here, and that's just when we run out of the last little bit of liquid, and it's all left in that container as gas. So we just boiled it away. This whole time, from the triple point up until this point here, like I said, we're boiling the liquid. It's in the liquid and the pressure were in equilibrium the whole time here. And then when we run out of liquid, we can no longer be at equilibrium with the liquid, and so we leave that PV area where it's sort of a strange parabolic shape, whatever. We leave that area and go straight into the gas phase, and so that's where we're up here, 3. So we had three marks before here. Let's see. Yeah, 1, 2, 3. That's all we had. Just making sure that the numbers correspond to what I had before. Does everybody feel a little comfortable with this? Any questions? Things I can clarify? The region in here, the supercritical region, is higher than the critical temperature, higher than the critical pressure, and a smaller volume. So this is the supercritical region. So above that critical point, you will not have a meniscus, but you could have a density that's liquid-like densities. You have that much material stuffed in there, but you're just at such a high temperature, you don't have condensation. Make sense? Okay, that's good. Oh yeah, this one I haven't done. This is D. So the other diagram I didn't show D, but this one I'm going to show D. Here we have, we're sitting at the same temperature, and I guess if we're going down, we're expanding the volume. So we're expanding the volume and dropping the pressure straight down, and here is all solid, right? All solid right there. Right here is solid, liquid, in equilibrium with each other. And so the solid's melting. So we have this container, we're sitting at the same pressure, so it's in some kind of pressure bath. We just start pulling on that piston and the solid starts to melt. And we keep pulling on it until where it's all liquid and the solid's gone. And we keep pulling on it and we're dropping the pressure, and here the liquid starts to boil. So we're pulling on it and it's boiling at that really low pressure, and then we pull on it so far that all the liquid's gone and we have just vapor. So do you feel like if I drew any line in these phase diagrams, you guys could walk along that line and tell me what's happening at each point? Okay, good. Because that's what I want you to do. That's the thing I fear, that we're going to feel comfortable about this today and then go somewhere for a week and then come back and not remember it. So just really try to lock this in. You're just reading charts in this whole middle part of the course. Now there's some restrictions on these phase diagrams. And water is kind of a weird one. Notice how when I pulled on the, if we do this one backwards, like I was pulling on the piston, shrinking increasing the volume and having the pressure drop. What if I pushed on it? So if I had a gas and I pushed on it and I pulled the heat out that I was adding, so it stayed the same temperature, eventually I could push it into the liquid phase, and then I could push in the liquid and push it into the solid phase. Water's weird. Okay, look what happens with water. Okay, let's just go right here. I push on the vapor. Let's follow this line right here. I'm at vapor. I push on it, and the vapor goes straight to solid. And then I push on the solid, and I'm pushing, and it becomes a liquid. That's weird, isn't it? So water has this really strange negative slope. So it has a negative slope to the solid liquid equilibrium line. And that only happens when the liquid is when the solid is less dense than the liquid. Right? So another way to say it is, if I push on the liquid, let's see. No, if I expand the liquid, it'll solidify. That's backwards than most other materials, right? If I expand on most materials, the liquid just gets less pressure. It doesn't solidify. But water will solidify. If you're at the right temperature and volume relationship and you pull on the liquid, it'll solidify. Another way to see this is ice, the solid phase of water, floats. And all the other substances in our everyday lives, there's like a few other substances where this is different, but every other substance that you will come across, the solid sinks. So if you have a chunk of aluminum and liquid aluminum, it's going to sink. Steel, same thing, but ice floats. Okay, ice expands, water expands when it freezes. That's really, if it didn't have that property, life wouldn't probably exist, because all of our soil is weathered that way. Rocks freeze and split apart. So this freeze-thaw cycle is really important in geology.
Ice was more dense than water, every time the lakes freeze over, it just drop a block of ice on all the fish.
Yeah, that's right. Yeah. I don't know how they survive. I think some have antifreeze in their blood, so I've heard. Yeah. And so this is just showing you that these different equilibrium regions, you have phases in equilibrium with each other. So in this case, P stands for phase, F stands for degrees of freedom. So if you're going to stay on this line, what does it mean to have a degree of freedom of 1? Well, if you're going to stay on that line, I can pick either temperature or pressure to change, but the other one is determined by the line. So like I have 1 degree of freedom, I can change the temperature, but I can't independently change the pressure. If I move temperature, if I stay on that line, then the pressure is picked. So it's like that's what we mean by degrees of freedom. Which one you have freedom to change? I could change pressure. If I want to stay on that line, then the temperature has to follow what I do with the pressure. If I'm out here in this region of, if I'm not on a line, let me just say it that way. If I'm not on a line, then I have 2 degrees of freedom. I can change the pressure and the temperature independently. But if I get on one of these lines, I have 2 phases in equilibrium, and so I've lost a degree of freedom. And this is a single component phase diagram. We could have mixtures. We have 2 components, and so it gets more complicated, and we'll get into that a little bit later. But I wanted to introduce this concept of number of components, that's C, number of phases, that's P, and degrees of freedom is F. And there's this thing called the phase rule. The degrees of freedom you have is the number of components minus the number of phases plus 2. Now I don't want to make too much of this equation, pretty simple equation, but this allows us to put boundaries on how we draw the phase diagrams. Let me show you an example. So in this 1 component phase diagram, I have these phases labeled with Greek characters, and this phase rule shows that we cannot have 4 phases in equilibrium right here. So that's an invalid point. So how does that play out practically? Like we might be collecting data on all these phases, and we could see, I can put a line through those data points, and it looks like this phase is going this direction. I measure this region. I draw a line through those points. It looks like it's going to this area. I measure this phase region. I draw a line through those points. It looks like it's going to the same point. And I measure this phase equilibrium, and I draw a line through that point. It looks like all 4 of those lines are going to intersect at the same point, doesn't it? But with the phase rule, I know that can't be the case. So one of these lines, it's like a game of chicken. One of these lines is going to move. So I've got to get closer to that point. And, maybe it's this one. Maybe the data here goes like this. And there's an intersection here and not this line right there. So that I still have 3 phases in equilibrium here and 3 phases in equilibrium there. So if I have 3 phases, I've got 1 component and 3 phases, then that's equal to 0. That means I have 0 degrees of freedom, and that's what these 3 phases in equilibrium have. They have 0 degrees of freedom, meaning it's a fixed point in pressure, a fixed point in temperature. So I can't move. If I want to stay on that spot, I can't change anything. If I change temperature or pressure, I'm not at that spot anymore. If I want to stay on a line, I've only got 1 degree of freedom. I can change temperature or pressure. If I'm in an open region, I can change both independently. So that's the phase rule. Let's move on. So let's look at some experimental phase diagrams. Here's the experimental phase diagram for water. We already kind of showed part of this one, but this has the numbers on it. So it's got the normal freezing point, the normal boiling point, 273.16 and 373.15. It's got the triple point, which is at 273.15 and the pressure of 0.006. And so those points are fixed in space by the behavior of water. We really don't have any degrees of freedom there. We can't change the temperature or the pressure because we won't be at the triple point. So it's a really strongly defined spot in these phase diagrams. But look at the y-axis. The pressure goes up to 8,000 atmospheres on this diagram. So how do I get 8,000 atmospheres on a diagram and still see the interesting stuff around 1 and 2? I've got to change the scale. And so that gray line, that's where we change scale. And so you see this line is really a smoothly varying line. It comes up to the critical point, but because we change scale, it looks like it's discontinuous. It looks like it takes a hard right turn, but it only does that because we've changed the scale. And so the critical point is way up here I don't have the atmospheres, but it's up here at 647.3 Kelvin, and then I guess 218 atmospheres. And then these are other phases of solid ice. So we have ice 1, ice 2, ice 3, ice 5, and ice 6. What's missing? Ice 4. So ice 4, I'll put a question mark there. It was, and look here, this is that thing I was saying about the phase rule. We know that phase exists because these 4 lines were coming into each other, and they can't have 4 phases in equilibrium if it's a single component. And so they, again, took a right turn or left turn, however you want to think of it, and there was a whole new phase of ice there. Now, I don't remember what portion of the diagram it was, but let's say they had another area here for ice 4. And then later, in repeating that experiment, they realized that ice 4 was really ice 5 or ice 3 or whatever. And so it didn't have experimental support. But by that time, they had already identified ice 5 and ice 6. So once again, like the 0th law of thermodynamics, we don't want to change the numbering system once it's been put in the literature. We just write an addendum and say ice 4 doesn't exist. So we kept ice 5 as ice 5 and ice 6 as ice 6. So it can be confusing, but it would be more confusing the other way. If we then tried to relabel ice 5 as ice 4, then we'd have conflicting data, and ice 6 as ice 5, it would be a really confusing thing in the literature. So they just left all the data for ice 5 alone and called it ice 5. So that's why there's a missing phase of ice. Now look at the slopes of these lines. This is kind of an interesting situation. I can have ice, if this keeps going along in the right, positive slope, eventually I'm going to have solid ice that's higher than the boiling point of water. Isn't that weird, just to conceptualize things? You think, how can you have ice in a solid phase above 100 C? Well, just change the pressure, right? If it's a container that's maintaining that pressure, you can heat that solid up above 100 C, but because you're at such a high pressure, it can't boil or melt or what have you. You change the pressure, now you're dropping down in this diagram, and you're going to go into the supercritical region, and then you're going to go into the gaseous region. Okay, maybe not the supercritical, but at least into the gaseous region. Okay, so that's the ice phase diagram. Notice it has this negative slope right here in this region. So in the region where we typically deal with, that's that negative slope. That's always a nice, simple thing to look for in a phase diagram. If you see that negative slope, it's water in your experience. Yeah. Let's look at another one. Here's CO2. Experimental phase diagram for CO2. Again, kind of a change in scale wherever that gray line is, but not as drastic a change in scale. Where's 1 atmosphere? It's right here. And notice this doesn't have a liquid phase at 1 atmosphere. So you can't have liquid CO2 at 1 atmosphere. The temperature of the, if you were to have dry ice in a container, maybe in a balloon where the pressure could stay at 1 atmosphere, so it's expanding and you've got the liquid and the vapor in equilibrium, the temperature of that dry ice would be 194.7 Kelvin. So 197 Kelvin, really cold. If you want, can someone subtract 273 from that? From 195, subtract 273. Negative 78, so that's Celsius. So negative 78 Celsius, really cold. That's why it's called dry ice, but you can get, it'll stick to your skin, it'll burn you. It will get on your skin and immediately freeze the moisture in your skin and then adhere to it. And it will cool your skin down to, what'd you say, minus 78 Celsius. and you'll get frostbite. That will destroy the cells, and then you get a blister, as your body tries to repair the damaged tissue. Same thing for liquid nitrogen, only I think it's 170 or whatever, 152 below 0 Celsius. And one time in August, we were filling a Dur with liquid nitrogen. We had a cold trap, and we're pouring it back into the main container for liquid nitrogen, and it hit the rim of the container, and I had cotton gloves on just to keep, because it was cold, right? So I had cotton gloves on, and it soaked those gloves with liquid nitrogen. And I turned to my lab mate, and I was like, take them off. And so she pulled the gloves off my hands, and my fingers were white. And so I slowly warmed them back up and everything, but I got frostbite on these 2 fingers. And so I had to wrap them up, and I went home for the summer before school started again, and Mom was like, what'd you do to your hand? I was like, I got frostbite. And she said, in August? I said, yeah, in the lab. So my recommendation in that situation is to use, if you want like insulating gloves, that's great. Cellulose or whatever, like cotton gloves, but put nitrile gloves over the top of them, because the nitrile would not have soaked up the liquid nitrogen. It would have bounced off those gloves, and then the insulation inside the nitrile gloves would have kept my hands from getting cold. But cellulose, like paper and cotton, will soak up liquid nitrogen like crazy, and it won't freeze solid. It'll just soak it up like a sponge. Like if you try to freeze paper and bust it, it won't bust. It'll just soak up the liquid nitrogen and just get really cold. So I don't know what that's called the glass transition temperature. When it goes below the glass transition temperature, it's more like a glass, and you can break it. So you can take a rubber hose and stick it in liquid nitrogen, get it really glassy, solid, and smash it. It'll smash like glass. And then it turns back to the rubber phase when it warms up to room temperature. It's a fun demo. Just be careful when you stick the tubing into the liquid nitrogen. It's a percolator effect, like a old style coffee pot, and it'll shoot liquid nitrogen through the hose. So if you're holding it towards you, it starts spraying you in the face or in the arm or whatever, and that's not fun. It's fun to show people, but it's not fun to have it spray on you. But paper won't freeze. Like you stick the paper in there, and it just won't get below glass transition temperature. Okay, look at this solid liquid line, positive slope. So if you were able to be at 67 atmospheres of CO2, which I don't recommend because it's really dangerous to be at that high pressure, the CO2 chunks of ice would be at the bottom and the liquid would be at the top. Here's the critical point. Here's the supercritical fluid region, solid, liquid, gas. Here's all of your temperatures. So CO2 does not have a normal boiling point. So not everything has a normal boiling point. At 1 atmosphere, it doesn't boil because there's no liquid. It has a sublimation equilibrium point. That would be this 194.7. Now, if you were to just put it at room temperature and let it come to equilibrium, you would see a liquid phase develop at this point here, but it'd be at 67 atmospheres. Here's a strange one for helium. This was the one that I did say, this was the one example of kind of a negative slope to that. This is 2 liquid phases, so that's really strange. We have a helium 2 liquid, superfluid, and a helium 1 liquid. But here's the solid liquid equilibrium line, and it's a positive slope. So when you look at this at first glance, you think, there's a negative slope, but it's 2 liquid phases, which is bizarre. Now, what's the difference between 2 liquid phases? The superfluid doesn't have a surface tension, so it's got a 0 surface tension. It will climb the walls of the container, and it's really kind of interesting. Really cold temperatures. Look at the Kelvin down here. So the critical point is 5.2 Kelvin. So we are definitely, in the supercritical region for helium naturally, right? So we're up here at the fully gas phase. Really at 1 bar, we're just in the gas phase. If we raise the pressure up, we can get in the supercritical region. So let's combine everything. Notice on the left is the PT phase diagram, and on the right is the PV phase diagram, and this is both combined. And so when I saw this, I fell in love with this diagram. And because it's the first time I saw both of those phase diagrams merged into one object, and I felt like I could understand it. Now, I love to see things in 3D. I've always worked on it my whole career, but it's difficult for students, so I made some 3D models of this phase diagram so you can look at all of the different angles and everything like that. This is my MakerBot. This is my new printer. So what I want you to do, let me show you. Look at it from this diagram. See volume, pressure. So that's the PV phase diagram. This is now pressure, temperature. That's the PT phase diagram. Yeah, very cool. And most of those lines on there are similar to the lines that we've drawn today with the pistons and the expansions and so on. Does that really help? Isn't that cool? Those are your state variables for that substance, water. Now look at the water, how the volume axis, how the solid takes up more volume than the liquid. You see how it's kind of a shelf? That would be reversed for other substances. But for water, it's kind of I don't want to say, but it kind of has a little lip on it. So this one that I've shown here, this is not water. It's got a positive slope to its solid liquid equilibrium line, and you can tell in the 3D phase diagram. There, let's see. Gotta find my pen. Okay, here we are. So this right here, this region right here, we're comparing the solid and the liquid, and it's saying that the solid fits into a smaller space than the liquid. You see that? And look at the water one. It's the reverse. The liquid fits into a smaller space than the solid on the V-axis. Do you see how the water, the phase diagram you have in your hands is really different than this? Look at this solid liquid area right here. That's where it's different. And so what you want to look at is the volume of the liquid versus the volume of the solid. Can you see it? Yeah, right there, the way you're looking. Yeah. So see how the solid is in a larger, on the volume axis, the solid has a larger number than the liquid. And then here, in this particular diagram, the solid has a smaller volume number than the liquid. Yeah. So on the volume axis, that's where you get your densities. That's where you're talking about density. So if you need to know the density of the substance, you pick the phase you're at, go down, look at the volume axis. If you know the mass of the substance that you have, say it's 1 mole, then you can find the density. Here, if we zoom in to the gas region, we've got the Carnot cycle. Okay, on that diagram, we've got isotherms and adiabats over here. Yeah, so that connects everything. So these are isotherms. Those are straight lines on the temperature axis, and notice the temperature axis isn't the steepest descent. So if you put a ball on that slope, it's going to go down an adiabat, not down a temperature. So the steepest descent line is the adiabat. And I did my best to draw it, but here's a little Carnot cycle shown. So these are the adiabats, and the isotherms. Yeah. And I've got it written over there in the far corner. Okay. Now, these are some terms. I wish we could just go in and rip the word bar out of science by the roots, because it just confuses things. If we just stick with atmospheres, we have normal boiling points, we have standard, temperature and pressure and all that. And so normal boiling point is 1 atmosphere. Why they've got to screw with that and have a thing called a standard boiling point with 1 bar, And now it's no longer 100 C, it's 99.6 C. Doesn't that want to make you want to hit somebody? Everybody in their world knows that water boils at 100 C, okay? But they don't know if that's standard or normal. So, I don't know. I have no patience with these people that you're like, well, we want everything to be SI. Well, just call ATM SI and just define it, right? It's 101,325 pascals. There you go. It's SI now. But no, they wanted 100,000 pascals, and so they call it a bar. And then it changes everything. And now it's 99.6 C for the standard boiling point, but it's 1 atmosphere and 100 C for the normal boiling point. I wanted to do a Kahoot at this point, but I think it's 8:50. Okay, but if you go to the Kahoot, you can look up the PT and PV phase diagram quiz on Kahoot. It's called the L20 phase diagram quiz. But if you go to chem_prof on Kahoot, and you search for 4449, you'll see all of our Kahoots. And this one, back in the day, was lecture 20. I think it's lecture something else today. But the phase diagram quiz is what you're looking for. So you can test your knowledge when we get back from spring break. All right, so that's good. And it has my favorite, as a little graphic, that's what you're looking for. So you see that, you know you're on the right one.